Algebra 2 Cram. New York State Algebra 2 Regents. Common Core, basic graphs of inverse trigonometric functions. The range of the inverse tangent of x. Concept number 18. The odds of someone doing exactly what you tell them to do is pretty slim, but I guarantee that if you cram with me, you'll become an Algebra 2 master. So inbox me at memedicine@gmail.com to order this complete cram session. Also spread the word to your friend and classmates who need to cram for Algebra 2 as well. They too can inbox me at memedicine@gmail.com for this complete cram session. And if this isn't the topic you're looking for, no worries. Still inbox me at memedicine@gmail.com for personalized packages. Now, if you attracted this cram session into your awareness, you're definitely above average and a super genius. In all honesty, you already know this. It's just a matter of peeling away the layers of virus code that's blocking your intellectual perfection. The Algebra 2 skills you want to develop are already perfectly developed. I'm just here to guide you in becoming aware of this by showing you how to think about Algebra 2 in a way that's going to get you optimal results, such as A's and perfect scores on your exams. Over a very short period of time, these cram sessions eliminate the virus code that blocks your awareness of your inner mathematical genius, okay? You're expanding your level of awareness by cramming with me. Now, why do you have to make an investment and order the complete cram session by inboxing me at memedicine@gmail.com? Well, this is something that you definitely might be asking yourself, and the reason is psychological. Investing in this benefits you more than it does me, because right now you might be marginally interested or even very interested in this topic. But when you pay for the complete cram session, your level of interest evolves into commitment. The kind that says, I'm going to get my money's worth out of this. And the kind that also reviews when it's not convenient for you, okay? Because commitment and accountability closes the gap between the intention of getting an A or a perfect test score and the actual result of manifesting your A or your perfect test score. The concept of cramming also has a negative connotation, but what people are actually thinking of is hurrying, which is the result of fear and can consequently be destructive for your learning process. We're not hurrying here, we're cramming. There's a difference. Hurrying is jam-packing tons of unorganized information into your mental or spiritual DNA over a very tiny amount of elapsed time, whereas cramming is taking quantum leaps in your understanding in an organized way that seems to have occurred over an instant. All right, so finally, let's delve into the concept of the range of the inverse tangent, sometimes referred to as the arctangent of x. Basic graphs of inverse trigonometric functions. The range of the inverse tangent of x, okay? And recall that the range is the set of all possible values of the dependent variable, usually referred to as x. But the key to progressing through this concept beautifully is to get things in order. So before we actually discuss the range of the inverse tangent of x, I want to give you a brief overview of where the originating function, the tangent of x, comes from, okay? Because the inverse tangent of x function is the inverse of the function y equals the tangent of x. Or here we're going to say the tangent of the angle theta, okay? All right, so this x is different from this x as well as this x. So temporarily, we're going to disregard the x here. This x here represents a tangent value. We're not thinking about that right now in our pre-example, okay? All right. So here we have our x, y Cartesian coordinate plane, and inscribed in quadrant 1, we have an acute angle. Okay, so let's examine this acute angle. Okay, so the angle is in standard position, And when I say standard position, I mean that it has all the following attributes. The vertex is located at the origin at 0. The initial side ray goes to the extent of its x-coordinate, which is on the positive x-axis, and the terminal side ray of this angle theta goes to the extent of the y-coordinate, and it has the magnitude of r. Now, r is the terminal side ray that the angle makes with the Cartesian coordinate plane. But if you resolve r, again, into its x and y components, what you have is the formation of a right triangle. And we can use this right triangular formation to discuss the concept of any trigonometric function, such as sine, cosine, or even tangent, okay? The reason why I'm using theta here is because we don't want to double or triple up on variables, because the x here is going to represent the x-coordinate. But most of the time, when you have the basic function, not the inverse function yet, you say the tangent of x. X is a variable usually used to signify the unlabeled angle, okay? But here we're using the Greek alpha theta, but I said or x because some people get confused if they've never seen the Greek letter theta before, okay? All right, so yeah, this angle is in standard position, and therefore the tangent of theta is equivalent to the y-coordinate, or the opposite side, the side opposite of theta, divided by the x-coordinate, or the side beneath theta. And you have to take note that the y-coordinate is positive in quadrants 1 and 2, but it could have been negative in quadrants 3 and 4, as well as the denominator, the x-coordinate. It's positive in quadrants 1 and 4, but negative in quadrants 2 and 3, okay? So these factors contribute to the sign of a specific tangent of a specific angle. For example, in quadrant 2, tangents are going to be negative because the denominator, the x-coordinates, are negative. In quadrant 3, tangents are going to be positive because the x and y coordinates are both negative, therefore making the overall fraction positive. And in quadrant 4, tangents are going to be negative because the y-coordinate is negative and the x-coordinate is positive, okay? Oh, and in quadrant 1, all the tangents are going to be positive because the x-coordinates are positive. Well, x, not y, and the y-coordinates are positive as well, okay? So this acute angle in standard position, and the angle is acute because it's written in quadrant 1, which is bound by the quadrantal angles 0 degrees and 90 degrees. So this acute angle, again in standard position, is referred to as a reference angle because when you start to calculate the inverse tangent, and just in case you forgot, all inverse trigonometric functions are going to yield the set of all angles whose tangent is x, or if this was the inverse sine, whose sine is x, and whose, or if it was the inverse cosine, whose cosine is x, okay? So it's the set of all angles with the value x as a tangent. And let me show you what I mean by that. Because this acute angle in standard position is a reference angle, sometimes called theta reference. Let me just indicate that really quickly. The lag time here is ridiculous. I'm really trying not to write. Okay, and what I mean by that is when you input the inverse tangent function, let's say x is, I don't know, 1, okay? That would mean that the reference angle is 45 degrees because the tangent of 45 degrees is equivalent to 1, okay? But 1 could also have been the answer for a tangent over here. I'm going to show you what I mean, okay? Let's say you were to flip this 45-degree angle do a vertical flip about the y-axis, and you ended up in quadrant 2. Pretend that ref is written here. I don't like to write it because of the lag time. It's going to take too much of our time. Your calculator, let's say you had 1 right here in this expression. Your calculator is going to calculate the value of the reference angle, which in our example is 45 degrees, okay? But what if you're not interested in this acute angle in quadrant 1? What if you're interested in its equivalent in quadrant 2? That is to say, this obtuse angle. Well, what you would have to do to find out the value of that angle, because your graphing calculator is not able to do it for you, at least most models. Maybe there's some newer models where you can specify whether you're in quadrants 1, 2, 3, or 4, but most models don't do this. What you would have to do is add the reference angle to the, subtract the reference angle, theta ref, from the extent of quadrant 2, and the extent of quadrant 2, as you already know, is the quadrantal angle 180 degrees. So 180 degrees minus theta ref is going to yield 135 degrees. And so the angle that you would be looking for if you're in quadrant 1 is 135 degrees. But then you also have to remember the sign based on the facts that I told you earlier. The sign here would be -1 because the x coordinates are going to be negative, okay? Let's take this concept to quadrant 3. Let's say you were to do a diagonal flip about the origin, and your theta reference is now located in quadrant 3. And again, let's pretend that you're not interested in our theta reference, which here is 45 degrees. Let's say you're interested in its equivalent in quadrant 3, which is going to be basically the extent of quadrant 2, which is the quadrantal angle, 180 degrees, plus your theta reference. So we're going to get a value of 225 degrees. So this is why this function is a one-to-many function, or it's called the set of all angles whose tangent is x, because in quadrant 1, theta reference has and a tangent value of 1, but every time you add 180 degrees to your original angle, you're going to get another angle who has the same value, or the same tangent value, that is, okay? So 225 degrees also has a tangent value of 1, but your calculator would not pick up on this. You would have to specify this yourself, knowing whether or not you're looking for the angle equivalent in quadrant 3. Last but not least, let's carry this concept to quadrant 4. Let's say you were to do a horizontal flip about the x-axis, and you wind up in quadrant 4. Your theta reference is over here. But again, let's say you're not interested in determining the value of this theta or theta reference. What if you're just actually interested? Oh, this lag time stuff is really annoying me. What if you're just interested basically in this humongous obtuse angle, which is the equivalent of theta reference in quadrant 4? Well, what you're going to do is subtract theta reference from the extent of quadrant 4, which is the quadrantal angle, 360 degrees, not 0 degrees, our starting point. It's a matter of doing a full revolution, okay? So 360 degrees minus 45 degrees, our theta reference example is going to be 315 degrees. So 315 degrees has the same numerical value as the tangent of 45 degrees. 1, but again, the sign is going to be negative because the y coordinates in quadrant 4 are all negative. Okay, So it would be -1. And again, we see that over here, we saw that 135 degrees had a tangent value of -1, but when we add 180 degrees to end up at 315 degrees, you also get a tangent value of -1. Hence, that's why this is a one-to-many function, but that can be problematic when determining the range or the domain of the inverse tangent function, okay? And let's just examine what the inverse tangent function does, or, how it relates to the tangent function. All right, so here we have our tangent of this angle theta is equivalent to the opposite side over the adjacent side, or you could say the sine over the cosine, or you could say the y-coordinate divided by the x-coordinate, since we're in an xy Cartesian coordinate plane. Now, when you apply the inverse tangent function to the entire expression, whatever you do to the left-hand side of the equation, you also have to do to the right-hand side. And we end up with the inverse tangent of y over x, which is going to yield the value of the tangent, equals the inverse tangent of the tangent of theta, or the tangent of x, if that's the variable convention you prefer. Okay, so the inverse tangent function basically undoes the tangent function to reveal the identity of the originating angle. So what you end up with is that the inverse tangent of y over x, and that's what this x value represents here, is equivalent to theta, the value of your angle, okay? Now that was a long aside or a long pre-example, but hopefully you're oriented. If you need to take a breather right now, definitely go ahead and do so. You know, come back to the rest of this later on. But for those of you who are brave souls who want to continue, let's go. Okay. All right. So what is the range of the function y equals the inverse tangent of x? Remember I told you earlier, sometimes this is referred to as the arctangent of x. And notice here that the a in arctangent is lowercase. That's different than from when the a is capitalized. And you'll see why in a moment's time, okay? So at this time, definitely press pause if you need to. And the way I want you to express your answer is by drawing it out on our graph system, okay? So go ahead and do what you have to do. And again, definitely press pause if you need to. All right, so the originating function y is equivalent to the tangent of x. This is the graph of y is equivalent to the tangent of x when you plot all the angle values on the horizontal or x-axis, and then you plot the actual tangent values on the y-axis. This is what the graph looks like. And again, this is not a one-to-one function. Rather, it's a one-to-many relation. So this is going to present problems when generating the range of the inverse tangent of x, because the inverse tangent of x is based on the originating function, the tangent of x. So what we're going to have to do basically is to restrict the domain, and the domain is a set of all independent variables or x variables of a function. Although the domain isn't what we're looking for here, we have to restrict the domain just to generate a legit function for the tangent of x. And when I say functions and one-to-one and one-to-many functions, what I mean is this, okay? You determine whether or not something drawn on a graph is a function by conducting the vertical line test. And whenever you conduct the vertical line test, that means that if the vertical line crosses the function at one place, it's a legit function. And then you can proceed and do all the beautiful mathematical things you want. But if it's not passing the vertical line test, this is not a function, okay? You can't do much with it. I just want you to keep that in mind, all right? So our goal here is to restrict the domain of the tangent of x so that our inverse tangent of x graph drawn can be a legit function. And in restricting the domain in the world of trigonometry and algebra 2, this can be done arbitrarily, but typically the domain restriction is done from negative pi over 2 radians to pi over 2 radians, or negative 90 degrees to 90 degrees. And this is going to be used as the one-to-one region to generate the graph of the inverse tangent of x, okay? And eventually, if you compare the arctan graph to the tangent of x graph, you'll see that one can be gotten from the other by interchanging the horizontal or vertical axes, or interchanging the domain and range, or just switching basically your x and y values. Now that might have confused some people, but let me illustrate what I'm talking about, okay? To create the graph of the inverse tangent of x, what you basically are going to do graphically is reflect the graph of the tangent of x across the line y equals x. So you're just going to flip this bad boy, like rotate it over the line y equals x. Now, it's really good to practice visualization in your imagination, and then you'll be able to see that the flip is going to yield this beauty right here. And this is the arctan of of x. And the reason why the a in arctan is going to be lowercase is because this is the one-to-one function between negative pi over 2 radians and pi over 2 radians, or between negative 90 degrees and well, now this is our radian axis. I'm going to show you what that is in a minute. Between negative 90 degrees and 90 degrees, whose values yield these particular tangents, okay? All right, I think I confused you, but don't worry, I'll show you when I neaten things up, I'm going to show you what I mean by that. This would have been arctan with a capital A. I'm not going to write out the entire arctan. Okay, this would have been a capital A if we did not restrict the function, and we basically ended up with something that looks like this. Try to imagine this as best you can, okay? And the problem here is that this wouldn't be a real function because the vertical line would cross the capital arctan function at several places. So it wouldn't even be a legit function that we could have a discussion about, okay? And when we neaten things up a bit, and remember we had to basically flip the tangent of x graph about the line y equals x, or basically switch the y-axis and x-axis from our tangent of x function. So we're going to see that the range, this is our answer, is basically negative pi over 2 to pi over 2 exclusive. Exclusive because pi over 2 and negative pi over 2 are not included in the range. Basically, this is going to continue forever in the positive infinity direction, and in the negative infinity direction, almost approaching, but never touching pi over 2 and negative pi over 2. Okay?